Hello friends. Imagine a model with 2.8 trillion parameters, the largest open-weight AI ever built, that just dropped quietly this week. No keynote, no big event. Just an overnight update to a website. That is Kimi K3, released by Beijing-based Moonshot AI on July 16, 2026. On independent benchmarks, it ranks behind only Claude Fable 5 and GPT 5.6 Sol, making it the third most capable model in the world. And in blind developer testing, it actually ranked number 1 for writing front-end code. Here is the question that should stop you in your tracks. How can a model nearly 3 times the size of anything previously released still be affordable to run? That is what we are going to answer in this video, and the answer is a beautiful piece of architecture called Mixture of Experts. To understand why Kimi K3 is remarkable, you first need to see the problem it solves. Traditional transformer models are called dense models. Dense means that when you feed a token, a single word or piece of a word, into the model, every single parameter in the network activates to process it. Every weight gets read, every calculation runs. If the model has 70 billion parameters, all 70 billion fire for every token. Now imagine scaling that to 1 trillion parameters. The compute cost per token scales with it. You get a smarter model, but each response costs dramatically more to generate. At 2.8 trillion parameters, a dense design would be economically absurd. The inference bill would make it impossible to offer at any practical price. This is the scaling wall that dense transformers hit. More capacity always means more cost per token, and there is no way around that trade-off, until you rethink the architecture entirely. Here is how Mixture of Experts breaks that trade-off. Instead of one big feed-forward network that every token passes through, you replace it with a large pool of smaller networks called experts. Each expert specializes in handling certain kinds of inputs. Alongside the experts sits a learner router, a lightweight network that looks at each incoming token and decides which expert should handle it. Only a small number of experts are selected and activated. The rest stay completely idle, so the model can have a massive total number of parameters across all its experts, giving it huge capacity and broad knowledge. But each token only ever touches a tiny fraction of them. Capacity and compute are now decoupled. You can scale one without automatically scaling the other. In Kimi K3, this plays out at a remarkable scale. 896 experts per layer, but only 16 activate per token. In the next slide, we will follow exactly what that means for a real forward pass through K3. Alright, let's follow a single token through K3 and see the router in action. When a token arrives, the router scores all 896 experts in that layer. Think of it like a dispatcher instantly ranking every specialist and picking the best 16. Those 16 experts light up and process the token. The other 880 do nothing. That is 1.8% of the expert pool doing all the work. Across the whole model, roughly 50 billion parameters activate per forward pass, not the full 2.8 trillion. That is the efficiency unlock. The router is also not naive. K3 uses a technique called quantile balancing, which spreads tokens evenly across experts so no single expert gets overloaded while others sit idle. The result is that Moonshot can offer a frontier-class model at about 94 cents per task, according to artificial analysis. Massive capacity, a fraction of the compute. But this clever design does come with its own costs. Now here is the honest part. MoE is not magic, and K3 illustrates its trade-offs clearly. First, memory. Sparse activation does not make unused experts disappear. All 2.8 trillion parameters still need to live somewhere in your serving system. Moonshot recommends at least 64 accelerators to run K3 in production. That is a data center setup, not a workstation. Second, there is a failure mode called expert collapse. The router, if left unchecked, develops a habit of sending most tokens to a handful of popular experts while ignoring the rest. Those neglected experts never train properly, and the model loses the specialization it was built around. K3 addresses this with quantile balancing, which distributes tokens based on score distributions to keep load spread evenly. Third, coordinating hundreds of experts spread across many machines adds real communication overhead at scale. These are genuine engineering costs, not theoretical ones. So with all that in mind, what does this architecture actually make possible? Here is the bigger picture. K3 is not just an impressive number. It is evidence that MoE has become the standard engine of frontier AI. By mid-2026, virtually every serious open-weight release uses sparse expert routing. DeepSeek V4 Pro, Qwen 3.5 and Llama 4 all do. And K3 shows what that unlocks. On the Artificial Analysis Intelligence Index, it scores 57, just behind the top 2 closed-source leaders but ahead of Claude Opus 4.8 as an open-weight model. Full weights are scheduled for July 27th under a modified MIT license, meaning anyone can study, run, and build on this architecture. That is the real shift. A year ago, frontier-class intelligence meant a closed API and a big bill. MoE is now handing comparable capability to the open community at manageable compute cost. The mental model to carry forward. MoE decouples what a model knows from what it costs to use. That is the engine changing everything. Thanks for watching, and we will see you in the next one.